Let's design a DC notch filter, digital filter, make it very sharp and then disturb it to see if it collapses. What do I mean by that? I mean by subjecting it to finite word length effects. Perhaps that pole being very close to the unit circle can be made to get too close and cause us trouble. So let me fold this away. Look at the tool we'll use. We use Sketch-a-Filt. It's already been set here to 500 samples per second, which is the sample rate of a problem seen in the social media recently, and we're going to try to comply with that, and also a very narrow 0.5 hertz bandwidth. Well, let's right click on the user def area and go and get notches and invoke them by such a click. Well, let's get the right sort of notch by right clicking on this menu to choose from many possibilities. Let's go for the most economical possible, which is a first order notch filter, and when I do, it comes up with 0, that is to say constant killing power, a notch frequency of 0, and therefore the coefficients will in this case be real. So all I'm talking about here is 2 real coefficients in the numerator and 2 in the denominator. The simplest design we could possibly go for. The other thing I need to do is set it to be a more narrow bandwidth. This is not sharp at all. I'm assuming that when this customer says he wants a bandwidth of 0.5 hertz, he's talking about a 3 dB down from the peak gain. So if I do this, the 3 indicates that it is going to be a 3 dB design. The width here is going to be, however, double-sided with this B. So half of that goes back into negative frequencies, and if I want 0.5 here, I'm going to have to put a 1 in this parameter box, and sure enough, I've got a very narrow filter indeed. Well, is it something I'm happy with? Is an ideal design? Let's examine it more closely. Move this over to the right and take this user def design, and put it into a more permanent area, the guest area, and take the only internal filter we have, releasing user def, and therefore this is now changed color to gray, and this is now our actual filter that we've designed, and user def can be used for something else. Let's see this more closely by seeing all filters we have, which at the moment is only 1. Move this over pretty far. Try to look at this in terms of dB. dB, pretty deep. Let's go down to -30 to start with, and zoom this in more closely to say 2 hertz, and sure enough, this is looking pretty good. I can see that it's coming down nicely, but let's look exactly at the 3 dB point, which is the real business end, and sure enough, that 3 dB down point happens at 0.5 hertz. So this is meeting the requirement, and we're quite happy with that. So let's go to the deep situation and consider what happens when I put these into quantized coefficients to see if I lose the goodness of this design. Well, I have a feature for that, so let me go to user def again and go up to finite word length effects, which is number 4, invoke that, and sure enough, I've got, with an 8-bit allocation of truncation, I've got a very poor green filter indeed. It's useless. No good at all. I'm going to need more bits. Well, what do I mean by the number of bits here? I mean that this is the number of bits devoted to the fractional part of the digital word, and with another bit for sign, that would really mean a 9-bit word, and that in principle would be enough because these coefficients are between 0 and 1 anyhow, so we don't need any extra bits allocated for integer portions. But still, 8 is just not enough to do the trick. So I right click on this and see with a slider what happens when I hit it with 9. Well, 9 is a whole lot better. It's coming down, but it's still no notch worth writing home about. So I pull this over closer and closer. 11, 13 is smack on top. And so with 13 bits plus 1 for sign, a 14-bit realization should do this. This is, of course, with quantization, but I can bring other types of design into play by going, for example, to rounding. It also holds up right on top, or round to 0, or even, convergent rounding. And so all those different modes of disaster have not caused this filter to crumble, and so it looks pretty good. So all we got to do is now take this design, export it to the workstation, take all these parameters, and then we can see them. Here's the guest filter, which is the ideal one. This is the one that we've approximated it with, and we could, for example, look at this, the A coefficients in more details, and you can see all the bits to all the fractional part of this out here. So we can, of course, export these, and we've got a good design.